Welcome. I love that you came in such a big number to a JDK security talk. I hope you'll enjoy it. And I hope to receive questions from your side, ideally at the end of the presentation, because I'm planning to cover quite a lot. So, a little bit about myself. I'm Anna. I'm working as a developer advocate in the Java team at Oracle. And you can find me on social media, on Twitter and on Mastodon at those handles that are there in the slide. And I would enjoy for you to ask me questions also via social media if you want to. After this talk, I can stay a little bit, but then I have to rush to the airport, unfortunately. And yes, I'm looking forward to your questions on security. So, JDK security, to be exact. The reason of the talk of today. Now, the Java language, you know, that was designed to be type safe and easy to use. It has many features that provide security benefits, such as memory management, garbage collection, range checking of arrays, and many more. So this reduces for you the overall programming burden and leading to fewer subtle programming errors or to have safer and more robust code. But there are changes that happen with each JDK release that are not that visible with a plain eye, let's say so. And the talk of today actually aims that to showcase those significant changes that occurred in the JDK security after Java 17. Now, to ease a little bit into the topic, in your opinion and from what you've heard, what would be a significant change that occurred with security in JDK after 17? You can shout it. No security manager. That's a very good one. Well, it's not exactly no. It's deprecated for removal, yeah. Other than that, that one got a jab, so it was quite prominent. And also a lot of people talked about it. Well, in that case, I'm gonna tell you a little bit more. So the JDK security impact is a little broader, and why we're so interested in JDK security as developers is because usually the lifetime support for a JDK version, like for example JDK 8, will potentially span for many years. JDK 8, 16 years plus. So over the time, many of the algorithms security algorithms that exist in the JDK become vulnerable and they can be exploited more easily. And the idea is, like with every release, to update the platform and to have changes in there so that you can safely build and deploy your applications using modern and strong cryptographic algorithms and many more. Now, this is the overall goal, this is the impact of the JDK security, and the talk is going to try to address what happened from 17 up to 21 significantly. But before diving into that, as Java security is quite a broad term, I would like to talk to you a little bit about Java security components, because in my slides you're going to see them from time to time, and I want you to have a diagram in your mind about where they are, what they mean in the Java security landscape. So, Java security consists of language and runtime security functionality. And it has a comprehensive set of APIs that cover many different areas, like you see here in the diagram. And the higher level abstractions of this diagram are built on top of the lower layer concepts, right? So you can see that in the diagram. The foundation, of course, is based on cryptography. So that's the first one. Now, the cryptography component, also called Java Cryptography Architecture, JCA, or Java Cryptography Extension, JCE, enables you to encrypt and decrypt data in Java, manage keys, and many more. Let me catch my breath a little bit. I'm a little nervous. Got some coffee before that. Now, next part is about the PKI component, which contains APIs and implementations for validating and building certification paths or certificate chains and storage of keys and certificates. Next one in the components part is this abbreviated component here, GSSAPI Kerberos. Now, programs can access security services via generic security service application program interface. That's what that acronym says, GSSAPI. And the JDK contains a GSSAPI implementation of Kerberos. Next in line, we have, of course, transport layer security component. Is also known as GSSE, like Java Secure Socket Extension, and contains APIs and implementations for TLS and DTLS. Last but not least in this row, signed jars. Now, signed jars allow you to apply a digital signature to a jar in order to signal that that jar has data integrity and authenticity. And last, and now I start with the other row, we have here the Java Generic Security Service, Java Generic Security Service, Simple Authentication and Security, and Java Authentication and Authorization Service, JAS. These are a series of frameworks and APIs for authentication and authorization. And in the row, last one, of course, we have XML signature that is containing APIs and implementation for generating and validating XML signatures. But apart from APIs and libraries, Java Security in JDK Security contains a small set of tools. These tools help you set security policies. So for example, we have Key Tool that helps you manage key store certificates, keys, and many more. We have Jar Signer that helps with signing and verifying a jar file. And of course, we have some tools for working with Kerberos like Kinit, Klist, Ktab. Each of them have a way to interact with Kerberos. Now, these are the components that probably you're going to see throughout the presentation being mentioned and what updates are on there. So hope that we are all clear on that and we are ready to start with what happened. What's the most important? Now, I spoke earlier that over time, all algorithms can be exploited more easily. Stronger algorithms and protocols are continuously being developed or they replace the weaker ones to provide an alternative. So in order to make our application stronger, a change that occurred with JDK 20, 21, and so on was increasing the key sizes to improve resilience of the cryptographic algorithms. So larger key sizes provide stronger cryptographic protection, and it's making it much more difficult for attackers to compromise data. And you have here in the table which algorithms changed and what's the value that they changed in their key size. Now, these cryptographic algorithms, they protect data and communication by using mathematical techniques, right, to ensure confidentiality, integrity, and authenticity. Yet the types of security threats increase with the advancement of technology, and we know nowadays we have AI, but we also have more powerful computers. And there's also the expectation of quantum computers becoming more easily for us to access. But there's also another side of thinking of quantum computers. If large-scale quantum computers are ever built, they can be used for breaking the widely used digital signature schemes like RSA, DSA, and many more. So what happened is that the IT industry has been working towards the goal of creating post-quantum cryptographic algorithms that are designed to be safe against an attack by either a quantum or a classical computer. Now, as these cryptographic algorithms mature, they are incorporated into the JDK as well, because they're new standards, right? So what happened is that, in consequence, Java 21 release brought also integrating the first post-quantum cryptography algorithm in the OpenJDK. And that one is called HSS/LMS. And I explained in the slide what HSS and LMS stand for. Now, the base of this algorithm is the Layton-Macaulay one-time signature that is signature scheme where a single private key can only be used to sign one message. So the security of LMS depends only on the security of the underlying hash functions. And it is believed that the security of the hash functions will not be broken by the development of large-scale quantum computers. That's why it's believed that this algorithm will be stronger. So SSH-LMS, SSS-LMS, sorry, HSS-LMS, the alliteration is tough for me to say, is one of the two quantum-resistant signature algorithms that have been standardized. The other one is XMSS. It's similar to this one, but it's less popular. Now, for use cases, this signature can be used for firmware signing because it's a kind of a sign once in the factory, but very often elsewhere case. So, apart from this, SSS-LMS requires that the key and signature generation be performed in the hardware, right? So in the hardware cryptographic modules, because those do not allow for secret key material to be exported. That's what makes it so safe against quantum computer aggression. On the other hand, verification is much simpler. So that was actually done in JDK 21. The SSS-LMS signature verification implementation. And if you're wondering how that is being done, how we can verify a signature implementation, that you can start by using a key factory implementation to read an HSS-LMS public key from its serialized format, for example, from a certificate in this case. And then you can verify if that signature uses the HSS-LMS algorithm via the signature implementation available with your specific security provider. If I would be running this with the OpenJDK release, the default provider would be Sun. That would be picked by this part of code. Give it a try. Now, these were the important changes that happened with the modernizing of the algorithm. So larger key sizes, a new new post-quantum computer algorithms and signature verification implementation. But what happens with those that are not that safe to use anymore? So there are algorithms that are weakening in the link of the security chain. So Java needs to limit and disable those, the usage of those, because you want to make sure as a Java developer that you are developing a robust application, right? And you probably have heard this many times, Java is secure. And yes, Java is secure most of the time by default. Yet, these changes are these enablement or disablement of the weakened algorithms are stored in the JDK security configuration file. So there are multiple security properties in the Java security file that allow you to control which algorithms are disabled in different areas. So you can be more strict with your application and have just certain algorithms that you know that are very strong to be enabled, and allow only those to be used in your application by configuring this file. And there are two different kind of properties that are listed here. So there are some algorithms that are disabled, and some of them are legacy, right? So disabled means that the configuration is restricts various functionality. But legacy means that you really shouldn't use that algorithm because they are likely to be disabled in a future JDK release. So that's the difference between them. Yeah, so this is like signal like which one is disabled and which one is legacy. And based on this configuration file, there are other features that can be seen in the JDK. So like disabling the SHA-1 jars, the jars that are signed with SHA-1 by default. So what happened in JDK 18 is that these jars were disabled by default. The reason being, as a long time ago, like in 2011, the National Institute of Standards and Technology, probably heard about NIST, well, they formally deprecated the SHA-1 usage. And in 2013, they said, well, SHA-1 should not be used in digital signatures in 2013 and is declared to be phased out by 2030. So what happened is that SHA-1 was disabled in TLS server certificates and XML signatures, but until JDK 18 to say so, you could still sign jars using SHA-1. However, thanks to this change, it's not the case anymore, and you get this warning, of course, when you're trying to assign your jar, but also when you're trying to validate a specific jar. If it has been signed with SHA-1, you get a warning that you are using a disabled algorithm, and moreover, it will be treated as unsigned, so you actually didn't sign it. To make sure that this change is not just for the late JDK 18 and above, these changes were also backported. That's why you see that little UFO there saying that, well, change introduced in JDK 18, but also was backported. So now make sure that others are going to benefit of it as well. Apart from disabling the SHA-1 jars by default, there were some weak algorithms for TLS that were disabled. Because 3DES cipher suits, they were enabled, they were removed from the default enabled TLS suits. And of course, 3DES and ARC4 are also not safe to be used, starting with JDK 20. Now, probably many of you have observed that you're not using TLS 1.0 or TLS 1.1 in your applications. If you're inspecting the TLS handshakes, you would see that that's not used. It's because they had various weaknesses, no longer recommended, and so on. But also, applications should use DTLS 1.2 instead of DTLS 1.0, because that one was also seen as having issues and being weak. DTLS 1.0, by the way, is disabled in Java security configuration file, the one that I showed you earlier, an example I showed you earlier. You can still enable it, but that's at your own risk. Now, in the beginning, I mentioned that there's also Kerberos, and there are tools for working with Kerberos. Now, because Kerberos also works with different algorithms, it has some restriction rules for weak algorithms itself. But Kerberos doesn't have the configuration taken from the Java security file. Usually it's taken from krby5.conf configuration file. And, is going to look over there for changes. For Kerberos itself, there were some encryption types that were removed. So first of all, starting with JDK 18, DES, 3DES, ARC4 encryption types have been removed from the default Kerberos encryption types. Now, these are weak encryption types. And you can see here on the left side an example of krby5.conf, and I want to explain it to you what happens with it. Now, they are weak, but if you would set, for example, allow weak to true, then any of the encryption types, any of the weak encryption types can be used. So many people are tempted to do that because they're like, okay, but my application still needs this. I feel that I still need this configured. So they would go and allow weak crypto to true just to have them enabled. The better part would be to selectively enable weak algorithms if you really need them by specifically adding the weak algorithm's name to the permitted encryption types. That's why you see the example here with the allow weak crypto to false, so that you don't enable everything, but you allow only some encrypted types with permitted encrypt types property, so that you filter what you know that is probably not that safe, or what you know for sure that, hey, would be good to use, and not use others that are unsafe. However, even if you're using this approach, because you need to, I must warn you that re-enabling any of these weak encryption types is not something that's recommended, and it's something at your own risk. So pay attention of the risks as well. Another thing to take into account, and we talked a little bit, well, actually you mentioned it, was the security manager. So you've seen the JEP, you've heard a lot that the security manager was deprecated for removal. It was pretty much present in a lot of discussions. But historically speaking, the security manager was a feature originally built as a sandbox for running potentially untrusted applets. Can you please raise your hand if any of you runs applets at this moment? Okay, so nobody's... I should ask, like, did you run an applet in the last 3 years? Okay, so it's an old technology that we probably didn't touch in a long time, right? The thing why security manager, let's say, grew inside of people was that because the initial implementation of it was later enhanced to support a fine-grained permission model. But even so, it was not very widely used. So a lot of people believe that, well, security manager is important because this has this fine-grained encryption model. But it was not that much used. So as a result, the security manager was deprecated for removal starting with JDK 17. And the reasons behind it, they are pretty easy to identify on why. Because, well, it had a brittle permission model, it was having a difficult programming model, and a poor performance. So, although since JDK 18, the property Java Security Manager is set to disallow by default, some people are still trying to put it on allow and have it still working if they have a dependency towards it. What you should know is that the security manager is still fully supported in JDK 17. But if you are using it, probably you've seen a lot of warnings that you're using it, so it's not very safe. But the reason why I'm talking about it is not just because, well, it was there, was deprecated for removal, was an important JEP about it. It was because inside the JDK, it had some ramifications. So some security API enhancements were driven by the fact that the security manager was deprecated for removal. And the JEP also said that, well, some APIs are using parts of that, even that sometimes they might not need it. But guess what? There is a connection, there is a dependency between them, and we need to find there is the need to have some enhancements at the level of the security APIs. So one of that was Java authorization and authentication and authorization service API. So there was a replacement needed there. Well, the replacement was for subject call us. Well, because what happened is, I'm going to show that in the code, subject doers was needing an intermediary object to get access to a subject. Well, that was not needed. And there was another change with subject get subject API, and now it has subject current in there. So let's look at the example. This is the old API, and this in old API you want to work on a particular subject. What happened here is that it required getting the access control context first, and then you would go and work and get the subject based on that access control. But you're never using the access control context further, so you just get an intermediate object, useless in this case. Now after the change, the code looks like this. So it's more like subject get current, no more intermediate object, no need of extra calls, and you get access to your subject very easily. Next, JDK 18 also brought an improvement on key store APIs. So there is a new get attributes for aliases method in the Java key store API. So before this change, and you can observe here in the code, the attributes of an entry could only be obtained if you're using the get attributes method of key store point entry. So you are going to a key store, you have to get an entry for that one. You have to, ideally, well, you know the password, and for the key store, you get an entry, and then you get access to the attributes of the key store based on that entry. Again, using an extra object just to get attributes of the key store. So, yeah, more simplification happening. Another change that came was that the API of customizing TLS and DTLS signature schemes. So JDK 19 came with the new APIs for customizing the signature schemes. And of course, this came as a complement for the JEP that was talking about implementing version 1.3 of Transport Layer Security TLS protocol. Yes, this is where you can find it, the new signature method. What this new API does, it helps applications customize the signature schemes for individual connections. And it provides granular control of the security properties rather than using what the security provider gives you as default signature scheme, because you might find throughout the way that you want to change that. Another thing that changed was API to customize TLS and DTLS named groups. And this change was introduced to customize and retrieve easier the prioritized list of named groups used to negotiate the key exchange mechanism in a TLS or DTLS connection. So we talk about API enhancements, and we talked about API enhancements of the level of looking at subjects and for the certificates, looking at TLS and DTLS customization. But let's get back a little bit to the quantum computer threat. So there's also a situation, well, when you need not just a new signature scheme, you might also think like maybe you need a new encryption technique for securing symmetric keys using public key cryptography. Because earlier we talked about algorithms that were vulnerable, right, to that. So maybe a new encryption scheme would also help in this case. And of course, the key encapsulation mechanism is one of those ways to protect ourselves against quantum computer threats. So as a result, in JDK 21, a key encapsulation mechanism API was introduced. Now, a key encapsulation mechanism is similar to other signature schemes, has public and private keys. But in this case, the sender is using the public key to create a ciphertext, which is called encapsulation. And it contains a randomly chosen symmetric key derived from the properties of a public key that was generated with a key pair. Now, unlike the traditional cryptography methods, this one does not require padding. So it takes a little bit less space. But moreover, in this case, if we are to look at an example of it, the sender creates an encapsulation using the public key, right? So that's the first step in it. Then the sender uses KEM to transmit the shared key to the receiver, right? Later, the receiver uses KEM to encrypt data using a symmetric algorithm, like in that case. And lastly, the receiver decrypts the encapsulation with its private key and can look at the encapsulated method thanks to that. So you can use KEM to first transmit your data, to first transmit the shared symmetric key, and later use it to efficiently encrypt data and using the symmetric algorithm. So it has like two steps. Okay. What are these components in the API? The key encapsulation mechanism API has like three components. One is the key pair generation function, which is already present in the Java Security API via the key pair generator API. There is a new key encapsulation function via the encapsulate that's being called like earlier by the sender, and takes the public key as input and outputs the shared secret key. And of course, key decapsulation on the other side uses the private key that is on the receiver side, and of course receives the key encapsulation message and can decapsulate that one thanks to the private key and make sure that they're receiving authenticated data from the right sender. Another change that came at the API level was impacting XML signatures. Now, XML signatures, if you remember the first diagram, we're pretty much the last block in the block diagram, right? So there were changes in the API for XML signatures to now accommodate signatures that can be to verify and sign with ECDSA algorithm. So what this means is that the standard signature, the signature method, there are new signature methods, URIs, like the ones listed here. And apart from that, you can toggle the XML signature secure mode, secure validation mode, and because, well, by default, the secure processing mode is enabled by default, but you can increase its strictness. Like we talked earlier about making the security of your application a little more strict thanks to JDK security configuration file. But you can be even more strict with your policies. And you have a few policies to do that. In that case, it's JDK XML D6 secure validation policy in this case. So if you're setting that one to true, this means that validation of XML signatures will be subject to stricter constraints as you define them in the secure validation policy for XML signatures. But apart from that, another change that occurred was that there's support for fine-tuning the usage of XPath here function. So here is not a standard XPath function. And what happened is that the upstream project has removed it, but yet a lot of XML signatures at this moment are still using that one. So in order to maintain the compatibility with existing XML signatures, there's a new property called here function supported. And the default value is to true to make sure that those XML signatures are using here still work. On the long term, this this signature might be deprecated for removal, so pay attention to it. Another change that occurred, other set of changes that occurred with JDK security are some operating system specific integrations. And typically these are available only for certain operating systems. And let's start with the popular operating system, Windows. Now, when it comes to Windows, if you're running this piece of code before JDK 19, you're going to get a very interesting output. What happens is that Windows stores keys and certificate for either the current user or the local machine. And you might need access to either of those, right? So for example, if you're using the Sun MSC API provider to access native cryptographic libraries or certificate stores on your Windows machine, you might get only certificates available to user accounts, right? So if you're listing only with those, you're gonna get, if you're using the Windows My example like here, before JDK 19, then in this case, you're gonna get only for the certificates for your current user. If you're running this code after JDK 19 with My Local Machine or Windows root local machine, you're gonna add access to your certificates on the local machine, not just for your current user. If you want your current user, you can use Windows My Current User or Windows root current users additionally. So these new key store types give you more granular access to the Windows certificates and keys. Now for Mac, the macOS key store, keychain store can show only trusted certificates. So before JDK 21, if you're running this piece of code, is going to print user domain certificates. And starting JDK 21 plus prints proper trust certificates in your user or admin domain. So that's the difference between it. Okay. And importantly, this change was also backported to JDK 11 and 17. There are also some updates to the kcerts file. So in this case, probably you have observed that the kcerts doesn't require, if you're using JDK 21, doesn't have changed it as default password as it used to be in the past. But also, It uses by default the PKCS 12 format, and if you're using JKS, for example, you're going to get a nice warning saying to you that, well, maybe you want to use the PKCS 12 format, as that one is a more popular format and is the default format for KCerts these days. Let me briefly talk about the updates on the tools that are for broader users, not the Kerberos ones. Now, in tools updates, there are a few improvements on key tool. So key tool, of course, now it also takes advantage of the larger key sizes, but it takes advantage of them when using, for example, the option of -gen key pair if you don't specify the key size. So if you're running such a command, by default, it's going to generate for you an RC key pair with the largest value. In this case is 3072 bits. Now, a next improvement to key tool is that -gensec key and import pass warn you if you're trying to use weak PBE algorithms. So what this means is that if you're using weak password-based encryption algorithms, you're going to get a nice warning, like in the example here. How does key tool know that? Well, is using the -keyalg option that you see there is -keyalg RC4 to understand that, hey, you're using a vulnerable algorithm when you're trying to use the -gensec key in this case. And last but not least, jar signer improvements. Of course, jar signer was also strengthened by default with this change in the signature algorithms when signing. SHA-1 jars we saw earlier, they're disabled by default. But also you can specify the class path to an alternate key store implementation via the option -provider path. So option -provider path was added in JDK 19, and you can specify that. In an example would be like here when running jar signer with a custom provider class, but also with a custom provider on a specific path. Another set of changes that occurred were for JFR, specifically with having more cryptography events and capture them when profiling or streaming JFR events. So the first one is JDK initial security property, and this one is enabled by default in the default and profile.gfc files that are shipped with OpenJDK. Now it captures the initial security property as they are loaded by Java security class. Well, historically speaking, there was another JFR event that was tracking the modification of the security properties. Now you also have a way to compare with what happened initially. So you get a better view of what was initially and what changed throughout the life cycle of your application with regards to security properties. If you want to disable it, these are the commands that you can use. So you can either use GFR configure to disable that, or you can either use the -XX star flight recording when you launch the application, and just say that, hey, initial security property, just disable it. Another event was recording details about security provider instance requests. So there's a new cryptographic event to identify and see how many times and how are the details of the security provider recorded throughout the life cycle of your application. So every time you're calling get service on the provider class, that is going to be recorded by GFR. But this one is disabled by default. So if you would like to enable it, these are two useful commands to enable it via GFR configure or on launch of your application. So I've talked a lot about changes and enhancements, but you should know that these are not randomly chosen. To make the evolution of security features within the Java platform more transparent, I want to discuss briefly the Java Crypto Roadmap. So the Java Crypto Roadmap was created to inform you, the developers, and the wider public about upcoming security changes to update releases. Now, each change of this in the roadmap is improving security in some way. So either, you saw earlier, restricting or disabling a weak algorithm, or a default has been changed to be a stronger setting, like the enlarged key sizes and for the algorithms. Or support a stronger algorithm can be added. Everything is documented there. So Every change that, so all these changes that I talked about, you're going to see that many of them are captured in the Java crypto roadmap, including the one about SHA-1 jars. And because these changes can be evolved throughout multiple releases, you can see a detailed log on how those were evolved. Yet, you've probably seen that changes come with compatibility risks. So when this kind of change is being proposed, it's not proposed just, hey, that's going to happen. That change is also coming with a notice, usually 3-6 months, but also comes with testing instructions if those are needed. So a way for you to detect like if that is going to work or not in your case. And as I'm a little less than 4 minutes away, if you're interested in JDK security and you also want to learn more about what's happening with Java, I would say to either follow the written part of Java in dev.java and inside.java. Inside.java promotes the latest news that happen, of course, inside Java, and what is not necessarily new, but what you should also be aware when using Java or certain features. But we also publish videos on the Java channel. So we are talking there about different subjects, including security and actually JDK security, so that you are have a better understanding of different concepts and you know how to employ them in your day-to-day life. The presentation had a lot of content, but there are more useful links for you to learn from. So there's also a video that this presentation is based on Java 21 security updates from 17 to 21. So there are some more updates that I didn't capture here, but they're on the video. There are some blogs that you should follow, like the one of Sham Millen. And of course, there are some jobs that I mentioned throughout the presentation, but you can find the link there so they're not lost. And last but not least, these are the slides. And of course, please rate the talk. Thank you for coming here and looking forward to your questions. And sorry for breathing so much. I will not drink coffee before my talk again. My heart is kind of pumping. If there are any questions, please raise your hand. I'll try to see you throughout the lights. Or we can talk afterwards a bit. Yes, there's a question there, please.
Yeah, the security algorithms.
Yes.
For me as a developer, sometimes it's not so hard, not so easy to tell where the algorithms come from, if they come from the JDK or from the framework or from some library. And so if we use, for example, very old Java, but we have like libraries that are bringing the algorithms, anything to approach this issue?
So as the question was from the developer's perspective, how can I identify which JDK security algorithm my application is using? First of all, I think that any framework looks first into the Java security configuration file. And something that I've seen with certain frameworks, they allow you to tweak which algorithms are allowed, which TLS version your application is using. So for example, I've seen this with Spring Boot, that it allows you to, let's say, force to TLS 1.3. Or for example, to like allow only certain signatures if you want to. There are specific security configurations that can be put in your application.properties. Now by default, I think that it also is at the latitude of the framework. I don't know the intrinsics of every framework and if they are changing anything additionally from the Java security file. But if you're interested in see exactly what you're using, you can always set the debug property and like for the security and say, I think it's javax.net.debug and say it equals to properties, and it will show to you what exactly is being taken by your application into configuration. But also the initial security properties, the GFR event gives you a good information about what are your security properties, thus meaning what algorithms you have enabled. So when you're streaming that, or if you're profiling that, you can see what you're using as well. So there are multiple ways, but the easiest I think is to set the debug. And you can, thank you. Any other question? Time's up. We can talk afterwards. Thank you once again, and enjoy the rest of the conference.